All right, I think I'll start recording about now. um, Big shouts out to Rex. They helped me set up all these commands that you see in the other way, top left here. So yeah, if you're watching this in the future or you're watching now, you can type any one of these things. You can get more information about the stream, more information about tutoring. Let me get rid of these for now. Okay, actually, let me just, for anyone that's just tuning in now, this is the book that we've been using. It's called Linear Algebra Done Right. And the author is Axler, and it's available for free on his website, Sheldon Axler. Linear Algebra Done Right. This is the 4th edition. I guess he just published this. I think I saw it was like a year old though, so I think maybe these are like, yeah, see, 2024. I think these are maybe some updates or some mistakes that he corrected or something. Okay. Right, so this is lesson 13, the third one in the series about linear algebra. So we basically just defined what an abstract vector space was. It was this thing where you could add stuff together and you could scale or multiply by either, usually real numbers or complex numbers, or generally, more generally, some field. Let me get the chat open. Let's see if anyone's. Yeah, the beloved linear algebra, of course. Yeah. No, I mean, I think linear algebra is probably one of my favorite subjects just because all of the theorems are very nice and you can sort of state things in a number of different equivalent ways. So if you don't like looking at something a certain way, sometimes you can reword the statement in a different way and, just has a lot for everyone, kind of, yeah. Is this Dr. Gold? Right, so lesson 13, this is going to be on linear independence. And originally I said, and we'd talk about finite dimensional vector spaces. That's kind of part of this section in this Axler book. But we'll kind of mention this. I guess I'm not going to really include it in the title, but yeah, we'll define what it means for a vector space to be finite dimensional as well, and we'll also talk about spanning sets. So this is kind of like a little bit more abstract of a view. We will do one problem where we solve it sort of in a reduced row echelon form sort of algorithm. But yeah, rank equals dimension. Oh, I'm missing these questions. I'll try to come back to those. Right, so first, Axler defines what is a linear combination of vectors. So if you give me a list of vectors from the vector space, what does it mean to take a linear combination of them, or what does it mean for a vector to be a linear combination? And so this is 2.2. And so we say a linear combination of vectors from some list, so v1 through vm, some list of vectors, m vectors. I guess he doesn't sort of, I guess he sort of implies it, but the list can't be infinite, so it has to be a finite list. So a linear combination of this finite list of vectors is some vector of the form a1, where we take a scalar a1 times v1, and then we add that to some scalar multiple of the next vector, etc. So linear combination is a vector of the form a1 v1 plus a2 v2 plus AM VM, where these A's are just some scalar value, so something from the field. So usually either some real number or a complex number. So AI is in the field for all I. And again, if you're not comfortable with this set theory, I won't use too much set theory notation, but I will use like the for all, there exists, like subset. Am I missing any of these questions here? Let's see. Oh, okay, you're just talking about the emotes. Okay, so we're just defining a linear combination here. So linear combination of some list of vectors is some sum where I'm scaling each vector by some scalar value from the field. It could be any scalar, it could be 0. I could sort of like not include one of the vectors by making one of the scalars 0. Like it could be 0 times v1 plus, right? That's allowed. Yeah, let's just do 2 examples, one from real numbers and one from complex numbers, just to make sure our head is on straight here. And I guess the picture you could think of is, if you want a picture for linear combination, you could think of if you have 2 vectors that aren't on the same line in like R2. Well, it's kind of hard to visualize in R2 since I'm going to get the entire plane, but maybe if I could draw in R3 and I could pick two vectors in R3, they could span a plane. So you could think of all linear combinations of them as spanning some plane. But here I can still work in 2 dimensions, but you know, if I get any multiple of this first vector plus any multiple of this second vector, you can actually get any other vector this way. Maybe this is a bad picture, but like if I pick any other vector here, it's some multiple of this plus some multiple of this vector. And it actually fills out the whole plane. Probably not the best picture, but we'll get more pictures in a second probably. Okay, and there's a notion of having the set of all possible linear combinations, and that's called the span of the vectors. So this is one possible linear combination here. If I let all the AIs vary over all possible elements of the field, then I get every possible linear combination, and that's called the span of the vectors. So that's the next definition. Okay, so definition 2.4. Pretty easy once we had the previous definition. So the span of a list of vectors is just going to be all linear combinations of those vectors. So usually I'll write this as like span v1 through vm. And this is just defined to be, we could just say in English, we could say it's all linear combinations of vectors, or we could just say it's the set of all a1 v1 plus a2 v2 plus am vm, where the AIs are in the field. Okay. So this is one particular linear combination. If I let the AIs vary over all possible elements of the field, then we get all possible linear combinations. And this is just the definition of the span of the vectors. And your intuition is sort of like in Fn, we have this standard basis of vectors. Remember, I went over them last time where there's only a 1 in the ith position and every other coordinate is 0. So those kind of, each vector represents a coordinate, and the span of all of the vectors gives you the whole space. So you're kind of building up the dimension of the space, assuming that every vector that you're adding is, actually outside of the space. So, of course, if you add a vector that's already in the space, then the span doesn't change. We could show that. I didn't write that in the notes, but that's one possible thing you could try to prove. Also, another thing that's fun about linear algebra is there's just so many easy things to prove that are actually kind of like informative, that really tell you something about the subject. So that's kind of nice. It's very accessible, is what I'm trying to say, I guess. Oh, I went to span and I skipped the linear combinations. Right, so span is all possible linear combinations, but I skipped the examples. Let's do a couple examples of a couple linear combinations. So the first example, the field is going to be the real numbers. So a real vector space, the scalars are real numbers, and the first vector, it's going to be a vector in R2. It's just going to be 2, 1. And so usually in linear algebra, he doesn't actually do this in the book, which annoys me like slightly, but he views everything in Rn as lists of vectors, but I like to write them as column vectors. I know that's like pretty standard, is to use the column vectors, because then you can just assume it's like a regular matrix and you can multiply it with another matrix and just use the regular matrix multiplication rules. So when I write a vector, I'll always write it like vertically like this. So this is a two-dimensional vector. The first entry is 2, second entry is 1, and our second vector is 3, 3. And then we might want to ask, so one possible linear combination is we take 2 times the first vector and we add 2 times the second vector, and we'll get another vector in R2. It'll be a list of 2 numbers. So in this case, I probably wrote this too big. Oops. Let me write it in another color. So 2 times v1 plus 2 times v2 is equal to, well, 2 times 2 is 4, plus 2 times 3 is 6, plus 4 is 10. And 1 times 2 plus 6 is 8. Hello. So yeah, we took 2 vectors in R2. They were lists of 2 numbers, 2, 1, 3, 3. And then we said, okay, so some linear combination of them, I could take any real number times the first vector plus any real number times the second number. I just chose 2 and 2. They didn't have to be integers. They didn't have to be positive. They could be -2 or -2.5. But I did 2 times vector 1 plus 2 times vector 2, and we got this vector. So considering I just wrote down the definition of span, we could say that this vector 10, 8 is in the span of v1 and v2. That would be some linear algebra terminology. Okay, so this is one example for the real case. Complex case. Complex case, it's basically the same rules, except now these scalars, instead of 2 and 2, I can pick complex numbers. Right? These are the numbers where you have some number I whose square is -1. So F complex numbers. Oops, lost my page. Okay, so now let's do V1 is now 2, I. V2 is 3, -3i. And now we can take a linear combination of these vectors, but now the scalars are complex numbers, so let's just apply some complex linear combination, just to say that we can. So the one I wrote down in my notes was 1 times v1 which is allowed, we can just multiply by 1. That is some linear combination. So 1 times v1 plus I times v2. And if I have enough room, I can fit this in. So 1 times v1, the first entry is 1 times 2 plus I times 3. So 2 plus 3i. And for the second component, we have I times 1. So I plus I times I is -1 times -1 is +3. So it's, 3 plus I. Okay, so again, now we have vectors in C2 instead of R2, so there's lists of 2 complex numbers. We still have, now we have complex vectors in C2, and we took some complex linear combination where we multiplied the first vector by 1 and the second vector by I. Then we took the linear combination. Okay, so this is linear combinations, and we said if you take the set of all possible linear combinations of a list of vectors, that's called the spanning set. And I don't think I'm going to prove it today, but you can prove that the spanning set is one of the things we were talking about last time, which is one of these subspaces. It's a subvector space or a linear subspace. It's a subset. It's like your notion of, you have a set and you have a smaller set within it. That's called a subset. Now you have this notion of you have some large vector space and some possibly smaller one sitting inside of it, and you call that a subspace. Okay, and then a couple more definitions. There's a lot of definitions in this section, but they're very important definitions. Basically, the whole foundation of linear algebra wouldn't make any sense without a lot of these. Is it turtles all the way down? Yeah, no, it's linearly independent vectors all the way down. Hopefully they're linearly independent. Or else you might need to get rid of some of them. Let's see. Okay, so so this is just a quick definition. What does it mean for a abstract vector space to be finite dimensional? He actually defines finite dimensional before he defines the actual number, the dimension, so that's kind of interesting, but he says that the 2.9, so a vector space is finite dimensional if there exists a finite list of vectors that span V, the vector space. So essentially, he's saying that we don't need to define this notion of dimension immediately. He actually defines it, like, I think in a section or two. Now he's just saying, okay, we'll say it's finite dimensional if I can come up with some finite list of vectors, and when I take all possible linear combinations of those finite vectors, I get every possible vector in the vector space. So in some sense, there's like some sort of notion of like a seed set for everything that's finite. So you can just write down some list of vectors, and every other vector can, in some sense, be created from that list as some linear combination. Subspace. Okay, so finite dimensional if basically we can come up with some finite spanning set. Right, and finally we get to the, hopefully the last definition for a bit. Yeah, it should be the last definition, which is linear independence. So when is a set of vectors or a list of vectors linearly independent? What does that mean? Maybe if you've taken a linear algebra class before, you've sort of gone through the computational route of proving like, okay, this list of vectors is linearly independent. So maybe you haven't seen it like in this abstract way before. Okay, so this is 2.15. Another definition. So now a list of vectors is linearly independent if and only if. So this is basically the definition. It's if and only if you have a linear combination that's equal to the zero vector. The only way that's possible is if all the scalars are equal to zero. So if and only if A1, V1, AM, VM equals 0 implies that basically all the AIs are equal to 0. Or in other words, or if I could, maybe I'm saying the same thing, but maybe I'm repeating myself, but so the vectors are linearly independent if and only if you have a linear combination that equals the 0 vector, it forces all of the coefficients to be 0. So in other words, there's no other possible way for some linear combination of the vectors to equal 0 other than the trivial linear combination. Sometimes we say it's the trivial linear combination, the one that always gives you the 0 vector, which is 0 times the first vector plus 0 times the second vector, etc., until you get to the last one. Right, so, and we also say that it's linearly dependent otherwise. So if there is some non-trivial linear combination that gives the 0 vector, then we say that it's not linearly independent or it's linearly dependent. And also, I just want to point out, last time I went over the definition of direct sum, we had a definition for the sum of subspaces, and there was a notion of direct sum. I just want to point out this was very similar to that condition we talked about last time, that it was a direct sum if there was some combination of the vectors, some sum of the vectors that equaled 0. It implied all the vectors were 0. So this is kind of similar, except now we're dealing with some linear combination instead of just some sum of vectors. But there is one thing we can say, which is that if these vectors are linearly independent, then the one-dimensional spaces spanned by each vector, if we take a direct sum of all of those, then it equals the spanning space. So I don't really want to waste the time to write that, but I think there's a problem in the end of 2b or 2c in the book where I think it's worded approximately that way, where if they're linearly independent, show that there's like some one-dimensional subspaces where the span of the vectors is equal to a direct sum over all of those one-dimensional subspaces. What am I missing in the chat here? Right. Actually, I'm going to write something similar here anyway. So let's see. Yeah, so this actually wasn't in the book, but I'm just going to include this anyways, which is, so if V1 through VM are linearly independent, then one statement that's true is that the span of the vectors can be written as a direct sum. So the span of v1 through vm, remember the span gives us some subspace, and this statement is saying that it's actually a direct sum where it's the span of v1, which is a one-dimensional space. I know we haven't talked about dimension yet, but span of v1, direct sum span of v2, direct sum span of vm. Yeah, and each one of these spaces is spanned by one vector, so you could use your imagination and say, okay, the span of one vector, that's all possible scalars of one vector. Well, in the real case, that's just a line. So we call these one-dimensional subspaces, but in the complex, you have to be careful about thinking about it sometimes, because when the field is like the complex numbers, your one-dimensional complex spaces are actually two-dimensional as real spaces. So there's this like mismatch with the dimensions. You need to be a little bit careful about whether you're dealing with the field over real numbers, complex numbers, or sometimes you have like finite fields, or algebraic closure of some finite field. Sum has overlap. Yeah. So the sum can have some overlap, but the direct sum, it only has 0 in common, but you do have to be a little bit careful, because you can't just check them pairwise that they have no intersection, or that they only intersect at the 0 vector. That's not enough to tell you that it's a direct sum. So you could have them. I believe you can have 3. This is actually a problem you could try to solve. Can you come up with 3 subspaces so that their pairwise intersection is the 0 vector, but if you take the sum of all of them, it's not a direct sum. So that's that's kind of a problem to wrap your head around the question. The question was, I did some reviews, so the sum has overlap, but the direct sum only has 0 in common. Yeah, so that's sort of true, but you just need to be a little bit careful about that. If you only have 2 subspaces, then it's always true that it's a direct sum if and only if they only intersect at the 0 vector. But if you have more than 2, they could be pairwise intersecting at 0, but still not be a direct sum. So yeah, just got to wrap your head around that a little bit. Right, so what was I saying here? So if you have some list of vectors, they're linearly independent, then the span of the vectors, which is a subspace, can actually be written as a direct sum. It's a direct sum over these one-dimensional subspaces, which is just the span of each individual vector. Okay, let's see. What else did I write here? Yeah, and then what's a nice easy canonical example of a set of linearly independent vectors? It's these standard basis vectors which I usually write as EI. So let me write this in a different color. Oops. So here's an example of a linearly independent set. And you can sort of think of this as like the canonical example of a linearly independent set. Like this is I think they call it the standard basis, right? So in Fn, so in Rn or Cn, real lists of real numbers or lists of complex numbers, you always have the linearly independent set, which is or linearly independent list, I guess. He uses lists because they could possibly repeat. So you always have the lists, which is E1, the first standard basis vector, E1, E2, yeah, and these are unit vectors. If you think of them in Rn, then they're unit vectors. Well, I guess they're unit vectors in Cn as well. So you just have zeros everywhere, except at the ith position you have a 1. Okay, so this is EI. Yeah, and then the list of all the EIs, that gives you a linearly independent set. Yeah, so why is that set linearly independent? Well, sort of like each coordinate doesn't see each other. So when you take some linear combination of them and you set it equal to 0, the only way that could happen is if each coordinate scalar was exactly 0, because nothing times 1 is ever going to be nothing times 1 will ever be 0 unless you're multiplying by 0, right? And since the coordinates don't really see each other, then it basically forces all the AIs to be 0 if you take a linear combination of these. But yeah, you'll see this. This is like standard basis vectors. You'll see this like over and over again if you study linear algebra. There's no way you can avoid this. This is usually like the basis that you fix that gives you, matrices in this standard basis, and then you could switch to a different basis and you'll have some sort of like change of basis matrix. But maybe I'm getting a little ahead of myself here. Okay, so yeah, just to review what I just went over. So you have linearly independent vectors, then the span of the vectors can be written as a direct sum over these one-dimensional subspaces. And also in Fn, which is like Rn or Cn, real numbers, lists of real numbers or complex numbers, we always have this special linearly independent set that we call usually like the standard basis vectors, and these are unit vectors in each direction of each dimension. So you have zeros everywhere, and you just go one unit in the direction of whatever the ith coordinate is, and we call that EI. That's the ith standard basis vector. Okay, and then this might be the last thing I go over, or second to last thing, but I kind of want to just solve like a computational problem. It's just going to be, take a list of vectors, show that it's linearly dependent. So we're going to end up having to do some sort of like by hand calculation. And I want to point out that this calculation method here that I'm using is, I'm not going to explicitly say that it's reduced row echelon form algorithm, but it's essentially, that's what I'm doing. I'm applying the reduced row echelon form algorithm in some sense. So I will go over this again, like all the rules of this a little bit more carefully, but here let's kind of pretend like we don't know what the rules are, and we'll sort of pretend like we're solving it just by, from scratch without using any sort of like rules. All right, so a big question in linear algebra is your teacher or the computer or whoever's forcing you to deal with linear algebra, they'll hand you a list of vectors, and the big question is this list linearly independent or is it dependent? Because usually if it's dependent, you want to get rid of there's some extra vectors in there that we don't need. We can toss them out of the list, and the remaining list spans the same set usually, if you throw out the right vectors, of course. Okay, so this is just an exercise. So one of the exercises from 2A. Get a different marker. So this is section 2A, problem 6. So we want to show that this list of vectors is linearly dependent. So we have 2, 3, 1. Or sorry, wait. 1, 2. Sorry, we want to show that this list is linearly dependent if and only if this last number c is equal to 8. So this is linearly dependent if and only if c is equal to 8. And sorry, if anybody's watching, are there any questions so far? So we're talking about linearly independent versus linearly dependent. You're given some list of vectors. The main question is it linearly independent? Is it linearly independent or dependent? Here they're asking us to prove that it's linearly dependent if C is equal to 8, and it's linearly independent if C is not equal to 8. Okay, so the if and the only if, yeah. Yeah, so if C is equal to 8, then it's dependent. If C is not equal to 8, then it's independent. So we have to actually show both. Yeah, so the sort of standard way to do this, there's like something called an augmented matrix. You could put all this information into an augmented matrix and try to solve it. I'm going to essentially be doing that in the background, but I'm not going to like, I'm not, well, I guess I essentially will be doing that, but I won't be calling it that. So we're going to take some linear combination of these. So a1 times the first vector plus a2 times the second vector plus a3 times the third vector. We're going to set it equal to 0 and see if we can figure out if there's an a1, a2, and a3. That's a solution, and it's going to depend on C in a way that we'll be able to write down. So let's just write down what I just said, and we're going to notice that it actually becomes 3 linear equations. So the first linear algebra class or lecture or whatever, I wrote down a set of equations and said the main study was trying to solve these linear equations simultaneously. So this is actually a restatement. Essentially, it becomes 3 linear equations that need to be solved simultaneously. So what are those 3 equations? So we have A1, I'll just call this V1, V2, and V3. So A1 times V1 plus A2 times V2 plus A3 times V3. This is A1 times 2 plus A2 times 1 plus A3 times 7. So we actually get 2A1 plus A2 plus 7A3. Right, because this 7 right here. Then we get 3 times A1 3 times A1 minus 1 times A2 plus 3 times A3. Also, if anyone notices any mistakes I make, please point them out. But I think I wrote it down already, so I should be good. And then the last component, we have A1 times 1 plus A2 times 2 plus A3 times C. So that's A1 plus 2A2 plus C times A3. And we're checking when this vector is equal to the 0 vector. So the vector that has all 3 components equal to 0. And so like I was saying before, essentially this problem just turns into the problem that we were solving the first day, which is, can we find some simultaneous solution such that the first component is 0, the second component is 0, and the third component is 0 for some A1, A2, A3. Again, C is some fixed number. We're just trying to solve for A1, A2, A3. So it really does just does become one of these simultaneous linear equation solutions where we're trying to solve these 3 equations simultaneously. Okay, so now basically we just reformulated the problem. We want to know, when does this have when does this have exactly one solution only, which is A1, A2, and A3 are all 0? And that's what we want to figure out. So still working on this problem. Any questions? Yeah, that's a good point. Yeah, also, if we can ever write V3 as a combination of V1 and V2, we automatically know that they're not independent. Wait, did I get the question right? Okay. Yeah, so essentially we just reformulated the problem. Now we're just trying to solve these three equations. When are they equal to 0 simultaneously? I wish I could copy and paste this up here. I'm basically just going to rewrite it. That's where the digital pad is good. Actually, so I'm going to rewrite those equations, but I'm actually going to flip the order of them. So you can kind of see that the order of the equations doesn't really matter, right? That's one of the rules for this reduced row echelon formula algorithm, is that when we have these systems of equations, we can reorder the equations, and the solution, it doesn't change the solution at all. So so I'm going to reorder. I'm going to write the same equations we had before, but I'm going to reorder them. So now we have the order A1 plus 2A2 plus C times A3, 2A1 plus A2 plus 7A3, and 3A1 minus A2 plus 3A3, and this whole thing is equal to the 0 vector. Yeah, right. And so the idea is that we want to be able to write A1 as some linear combination of the other vectors, and then replace the A1 in the other equations with that linear combination. And what we're going to end up with is I'll only have an A1 in the first equation, and I'll sort of have deleted it from the second and the third. And we want to kind of just do this over and over with and delete as many variables from each row, so that there's like basically as few variables as possible in each row. That's sort of the idea. So here we're going to isolate A1 first, and we're going to delete the A1s from the other rows. Then we're going to try to isolate A2 in the second row, delete the A2s from the other rows, and then same thing for the last one. We're going to try to isolate the A3 here, and then delete the A3 terms from the other two. So if you haven't seen this before, this is essentially the reduced row echelon formula algorithm. I'm just not really writing out the steps explicitly, but so one of the things we already sort of applied one of the steps which was that we swapped, or we sort of changed the order of the rows, or changed the order of the equations. So now I have an A1 here, and another thing that I'm allowed to do, so really there's three rules. Let's write them down. So we can swap rows or change the order of rows. We can multiply a row by a constant, one of the scalars from the field. So we can multiply row by a constant lambda in the field. So like up here, if I wanted to, I could just multiply the whole last row by 4, or really any number, right? Well, I think it should be non-zero maybe, because we don't want to multiply by 0. And then also we're allowed to add or subtract some multiple of some other row to another row. So we can take like the third row, and I can subtract 2 of the second row from the third row. So that's the third thing we're allowed to do. Add or subtract a multiple of one row from another. All right, and these are the three, I don't know what these are technically called. These are like the 3 reduced row echelon algorithm rules. I forget what the precise technical name of them is, but essentially when we do any one of these 3 operations, it doesn't change the set of solutions, because if I change the order of these, that's not changing anything about the solution, right? I'm just kind of looking at them in a different order. If I multiply a row by a non-zero constant, I could always undo that by multiplying by the inverse. And so in some sense, I haven't changed the set of solutions. I just applied some invertible operation that I could undo. And same thing with adding a multiple of one row from another. Again, if this is equal to 0, then I can multiply this by anything and add it to another row, and I shouldn't be changing the solutions. In fact, you could undo that also by just subtracting that multiple of the other row. And we know that the left-hand side and the right-hand side are equal, so when we add or subtract a row, we know that the equality is upheld because the left-hand sides are equal, the right-hand sides are equal, so when we add them together, we still get equality. The matrix can neither be created nor destroyed. Okay, so as long as we do one of these three things every time, then the solutions don't change. And like I said, we sort of want to, the process is you want to eliminate as many variables from each row as possible. So you want to isolate the coefficient here, or you want to create a 1 in the coefficient here. So if there wasn't a 1 here, I would want to divide out by whatever this first coefficient was, but it's already equal to 1. So now I can take the first row and I can subtract 2 of the first row from the second row. That's going to eliminate this. Get another color. So if I subtract, if I subtract 2 of the first row from the second row and I subtract 3 of the first row from the third row, that's going to eliminate these two terms. Because 2 times a1 is 2a1, and when I subtract that from here, that's going to be 2a1 minus 2a1. That's going to cancel this 2a1, and when I subtract 3 of the first equation from here, I'm going to get 3a1 minus 3a1, and that's going to cancel the 3a1 here. So essentially, the process is you want to swap your rows until you have the leftmost variable at the top. In this case, we have variables in every row, so I really didn't need to swap. I could have just divided out, but then you get the coefficient here equal to 1, and then you subtract off all of the other variables from every other row for that particular variable. Then you move to the next variable and you do the same thing, and it's sort of just this iterative, recursive process. It's possible you don't have a variable in, like, for any row. That's okay. So I will, yeah, I'm not going into every possible thing that could possibly happen right now, but yeah, let's just try to work on this particular problem. So we eliminate the 2a1, we eliminate the 3a1. Let me write it out fully. Okay, so we're subtracting 2 of the first row from this row, and we're subtracting 3 of the first row from this row. That leaves us with a1. First row doesn't change. This becomes 0a1, so 0. 2a2, or sorry, 1a2 minus 2 times 2 is 4. So 1 minus 4 is -3. And then 7 minus 2c, right, that's what I had, yeah. Times a3. And then the last one is -1 minus 6, so it becomes -7. Yeah, wait. Oh, I have it out of order. 3 minus 3c. Right, and then 3 minus 3c times a3. So that's the last term. And you can see now I've eliminated the A1 from the second and third row, and now the second and third rows equations only have A2 and A3. All right, and now I go to the next variable, which is A2. So this coefficient is not equal to 1, so I can divide this whole row by -3. And just to save some time here, I'm going to just do the division here by erasing. So -3 divided by 3 is 1. And then I just divide this by, so negative and then divided by 3. Yeah, I'll just put the 1/3 in the front. So I didn't have a 1 in front of here initially, but I can always multiply or divide any row by whatever the coefficient is to make it 1. So I just divided by -3. Now we have a coefficient of 1 here. And now I can add and multiply, add multiples of this row to other rows to eliminate the A2 here and the A2 here. So what I can do is I can add 7 of the second row to the third row, and I can subtract 2 of the second row from the first row, and that should eliminate this 2A1, A2 here, and should eliminate the -7 here. I know I'm going a little long here, but I think this problem is very illustrative of how to do this algorithm. So first we eliminate the A1s, now we're eliminating the A2s. So we get A1 plus 0, or I'm just going to leave out the zeros. So A1 plus 0 plus -2 of these. So it'll be C, C plus 2/3 times 7 minus 2C, all times A3. Then A2 plus minus 7 minus 2C over 3 times A3. And then it's kind of hard to see, but the last row is just 0 plus 0 plus, and then it has this long thing times A3, which is, so 0 plus 0 plus 3 minus 3C minus 7/3 times 7 minus 2C, all times A3. So it's a little bit cluttered here, but essentially we just have this giant number here times A3. And the idea here is if this number is equal to 0, then we could multiply any A3 by it and still get 0. So really this if and only if statement comes down to whether this coefficient at the bottom in front of the A3 is equal to 0 or not. So that's all we have to check. Right, so what we have to check is this number here at the bottom, 3 minus 3C minus 7/3 times the quantity of 7 minus 2C. If that's equal to 0, then the vectors are dependent. If it's not equal to 0, then I can divide out by this and finish the algorithm, and then that means that they're linearly independent. Okay, so all we have to do is let's check when this number is equal to 0 and when it's not equal to 0, and hopefully that's exactly if and only if C is equal to 8, and that will solve our problem. So hopefully if you're watching this later or in the future, you're just doing this problem on your own and you can sort of check your work with this, but so that last coefficient in front of the A3, we had, it was 3 minus 3C minus 7/3 times 7 minus 2C. And we said that the vectors were dependent if and only if this was equal to 0. So that's if and only if, now we just have to solve for c, right? So what is this? 3 minus 7 squared over 3 minus 3c plus 14 over 3c equals 0, which is if and only if. Now I have to do some basic math in my head. Who can do this for me? So what is this? 49 over 3. Oh, God. Is that 27 thirds minus 49 thirds? No, sorry. Ugh. 27 times 3. 27 times 3 thirds minus 49 thirds. So what is that? 81 thirds. 81 minus 49. 32 thirds. Did I do that right? All right. Might need to double check this, but I think it's 32 thirds. Well, we'll see it once the answer at the end is correct or not. So minus or plus -3 minus 14 thirds or 9 thirds. Minus 9 minus 14 minus 25. So minus 25 thirds. Times c equals 0. You can see I didn't do this out in my notes. This is the only thing I didn't do out. Right, so then you can move this to the other side. 32 thirds is equal to 25 thirds times c. What did I do wrong? 32 equals 25c. No, that can't be right. I did something wrong. All right, so now yeah, we're doing it live. Yeah, but I don't think that's the right answer. So yeah, I did something wrong earlier. I'm trying to do fractions in my head. That's the problem. Here, let's type it in Wolfram Alpha real quick. Actually, I could probably just someone do this out for me. What did I do wrong here? 3. Oh, 3 times 27 is 81. Yeah, that's right. 81 minus 49 is 32, right? 32 thirds plus minus 3 should be, oh, okay, yeah, I know the second number is wrong, right? Yeah, there's no back button. All right, well, yeah, it's always the fractions that bring me down, of course, the simplest of the math. I think this fraction right here is wrong, though. First one's right. So it's minus 3 plus like 4 and 2 thirds. So 1 and 2 thirds. So 5 thirds c. Okay, maybe that's right now. And this equals 0. Oh wait, no, it has to be positive, right? Or it has to be negative. Oh, minus 3, right? Yeah, minus 3 plus 4 and a third. Oh, wait. Okay. So no one can figure out what I'm doing wrong? So 3 minus 3c minus 7/3 times 7 minus 2c equals 0. Okay. It's 3. Yeah, I know. 3 minus 49/3. Okay, that part I think is right. Minus 3c plus 14/3 c minus 3 plus 4 2/3 is 1 1/3, but the answer's not negative. Wait, okay. This is like wrong earlier. 4 2/3. Where was the error? 4 2/3. Oh. 4 2/3. Yeah, minus 3 plus 4 2/3 should be 5/3 though, right? Okay, maybe I did some of the math earlier though. Wrong. Five-thirds, yeah. Yeah, but then this doesn't make sense because then c would be negative, but we're trying to show that c is 8. So I'm assuming that maybe I did something wrong with the math earlier. Wait, no, I thought I had checked this and it worked because I plugged in 8 for c and it worked. 24. So 3 minus 24 minus 7/3 times 7 minus 16. 3 minus 24 is negative 21 minus 49/3 plus 16 times 7/3. I'm just going to check this real quick. Yeah, it is 0. Yeah. Okay, so I don't know. What am I doing wrong here? Okay. 14 minus 9 over 3 is 5/3. 9 minus 49 over 3 is 40 over 3. Yeah, so c is equal to 8. So which one of these numbers here is wrong, though? Because, I mean, this can't be right, because then c would be negative, right? So 3 minus 49/3 is this, right? Correct? 32. Oh, okay, I see. Negative 40 over 3. 3 times 3. Oh, okay, yeah, sorry. I did 27 times 3. Thank you. Right. No, I know. This is the only thing I didn't write the answer down for. Yeah, I know. Of course, I knew this was gonna happen. Negative 40 over 3. Right. So 27/3 minus 49/3. Wait. No, I keep doing this. 81/3. Why am I not able to do 27 times 3? Isn't that 81? No, I know. The struggle makes it more real, right? 9/3, right. So brain dead. Sorry, guys. Okay. Well, as long as we all agree. Okay, so 3 minus 7 squared over 3, that's negative 40/3. Then we have minus, we had it before, right? It was 5/3, I think. Or plus 5/3. C is equal to 0. So 5/3, this is if and only if 5/3 C is equal to 40 over 3. So 5c equals 40, and therefore c is equal to 8. So if and only if c is equal to 8. Okay, right. move this to the other side. So 5/3 C equals 40/3. So 5C equals 40, C equals 8. And this is if and only if. So, right, when we're doing the reduced row echelon form, essentially that coefficient at the end, if it's equal to 0, then we get dependence. That's if and only if C is equal to 8. And then if C is not equal to 8, then this number is not equal to 0, and then we get independence. Okay, sorry, I just had to complete it. I know I took a lot of time there, but thanks everybody for sticking with me and helping out. Any other questions? I'll stick around and answer them if I can.